My name is RyanGrammer, and today we'll be looking at predicting areas of debris flows in recently burned areas using precipitation forecasts. First off, we want to start off with what is a debris flow? Debris flow is fast-moving mass of water, rocks, soil, and some other debris that can move downhill, usually through a drainage catchment, and that's often triggered by heavy rainfall. It can collect many things on its path, trees, branches, utility poles, even vehicles. These debris flows can reach speeds of up to 35 miles an hour, and the mass of the flow can pick up those large objects and cause some serious damage. They differ from flash floods as they carry a large amount of solid material, making them much more destructive. Here's a photo from 2018 in the Montecito debris flow. This one was pretty devastating, and as you can see, there's some boulders that were as large as 20 feet in diameter that were swept into the flow, caused damage to this house. Let's talk about some of the effects of a debris flow. As you saw in the last slide, property damage. We also see injury and loss of life. Debris can cause fatal injuries through blunt force trauma when it hits a person. Um, People are also swept away and they drown trying to escape the debris flow. We can also talk about road closures and roadblocks. These obscure rescue efforts from first responders, and the force of debris flow can easily wash away a road, leading to alternate routes to be able to open to go places. And then utilities damage. Um, Debris flows can knock down power lines, poles, interrupt transformers and other electrical infrastructure, disrupting service for communities. Erosion from the debris flows can undermine the integrity of gas lines, leading to possible gas leaks that have the potential to start a fire or cause some issues. Sewage lines can also be affected when the lines get blocked or destroyed. And we're going to look at some of the main factors that cause a debris flow. These are precipitation, slope, and soil composition and vegetation. First off, we'll look at precipitation. Debris flows, like I said earlier, are usually triggered by high intensity, short duration bursts of rain. So as the water from precipitation starts to run downhill, that will pick up soil, small rocks, and other debris, and this will increase rapidly in size and intensity as more precipitation falls. Take a look at slope. So steeper the slope, the easier a debris flow starts. They provide less resistance to the contents of the debris flow as they move down the hill. And the force of gravity really accelerates that movement of the materials flowing down. And debris flows usually originate in areas where slopes are steeper than 25 to 30 degrees. We'll also look at soil composition and vegetation. Roots are holding the soil into the ground, and without them, the soil becomes loose and can wash away the soil in a debris flow. So we're looking for areas with little vegetation, stabilizing the soil because they have a greater risk of erosion and debris flows. Yeah, and one of those areas is recent burn areas. They have little to no vegetation with roots to hold soil down as they've been burned. Burned areas also tend to absorb less water because the burned organic matter condenses to form that water repellent layer, increases the surface runoff, and will pick up some of those organic material, soil, and stuff that's on the surface. The same intensity of rain can generate overland flows more than 10 times greater in areas recently burned compared to those without fire. I thought that was an interesting fact. So goals and objectives for this project, inform the public about where debris flows are more likely to occur. This will allow them to create a plan and be prepared in the event that one does happen. Also, utility companies, we want to let them know where they're more likely to occur so that they can strategically place crews to assist in getting those utilities back up and running. And also the local government and first responders so that they can plan in case of an emergency and plan ahead so they can do some road closures in areas that are going to be highly likely. Our study area here is in Southern California. We're looking at 10 counties here. The reason we chose Southern California is because its climate, it plays a big part in how often wildfires and debris flows occur. Southern California has a really hot, dry summer that will clear the vegetation of moisture and will provide the fires the fuel to spread. And also, in the later months of the year, the Santa Ana winds can start in fuel fires, as we saw with the Palisades and Eaton fires that occurred earlier this year in Los Angeles County. Then that season's followed by a couple wet months, where 75% of California's annual precipitation falls from November through March. And that combination of barren land after the fire, along with a strong rainstorm, is the perfect concoction for debris flow to occur. Just a little bit of facts about Southern California. These counties cover a little over 55,000 square miles, or a little over 1/3 of California's total size. And as of 2020, these 10 counties had a population a little under 24 million people, accounting for 60% of California's total population. Take a look at the data sources that we're going to use here. We're going to be using the National Weather Service precipitation forecast. This layer has the cumulative or total precipitation predicted in the next 72 hours. We'll also use the elevation derivatives for national applications. It's a hydrologic database derived from a version of the National Elevation Dataset. It provides us with the slope layer as well as a layer with individual catchments where those debris flows can occur. Also use the historical fire perimeters to get recently burned areas, the roads national DO database to see which roads are affected, and the national substate geography geodatabase for the county layers. Our methods here, we're going to prepare the data to be ingested into the project. We're going to use ArcGIS Pro's model builder to create a model that runs every 6 hours to update the precipitation data. Then we're going to publish that resulting layer to ArcGIS Online and create a web map, and then use that web map in a dashboard. First off, we're going to buffer the fire perimeters layer 1,500 feet to account for any islands or unburned areas within the fire perimeter. Then we're going to take the slope layer and average the slope values in those specific catchments from the EDNA database, calculate those and add those to the catchments feature class as a new field. Then we're going to clip the extent of the fire perimeters or the catchments layers to the extent of the fire perimeters layer, as we're really looking for the recently burned areas where debris flows can occur. And finally, we're going to join the fire perimeter attributes to the catchments feature class based on the intersection of these two data sets using the spatial join tool. And then that tool will give us the affected catchments layer. With this affected catchments layer, we're just going to run a quick summarize within tool to summarize the length of primary roads, secondary roads, and local roads within each affected catchment area. And the tools run 3 consecutive times to cover each road layer, where primary roads are interstates and major freeways, secondary roads are highways and state routes, and local roads are local streets and back roads. Here's the model that we used. Starting off on the left-hand side, we exported the precipitation layer, the cumulative total over 72 hours predicted, to a feature class, and then joined those features using a spatial join to the affected catchments layer, or that layer that all the catchments that have been affected by recent wildfires. And this took into account that some catchments could have had multiple predicted values based on how large their catchment was. So the average precipitation was calculated for each one. We also added and calculated a new field, likelihood, that assigns a value to how likely a debris flow is to occur. And we'll take a look at how we calculated that in a couple seconds. Finally, we deleted some unnecessary fields from when we exported the precipitation layer, and then we published this layer to ArcGIS Online. Like I said, this is ran every 6 hours to keep this data continuously updating. Here's how we're calculating the probability of a debris flow in each catchment. Like I said, there's 3 main variables that are used that contribute to a debris flow. That's predicted precipitation, the average slope in each catchment, and how recent the area in that catchment burned. So we assigned 45% for the predicted 45% weight to the predicted precipitation, 30% weight to the average slope in the catchment, and a 25% weight into the how recent the area burned. So predicted precipitation, these are separated into categories based on how much precipitation is predicted and then assigned a value for that. So the higher precipitation forecasted, the higher the value is returned, as you can see in the table below. We have average slope of each catchment. This is weighted the second heaviest of the three variables. Debris flows are more likely to happen on slopes that are steeper than 25 to 30 degrees, as I mentioned earlier in the presentation. But we're taking into account areas in the catchment that are flatter and not just the slope. So we're going to adjust our table here a little bit to take into account those that we're going to have some flatter areas in the catchment. And then like the precipitation values, the higher the average slope value in the catchment, the higher the returned value is. Then we're going to take a look at how recent the area burned. So we're looking for fires that have occurred in the last year. These areas will be still trying to regrow their vegetation compared to fires that happened more than a year ago, where those areas may have more established vegetation. And each of those three were calculated using a Python script, and that was in the Calculate Field tool in ArcGIS Model Builder. Next, we'll take a look at the web map design. So this was symbolized to cater to our audience. Because the public, we want to make sure that all our symbology was easy to read. So we have our affected catchments with a range from very low to high, where very low has a nice neutral color, where high has a warning color of red. And each of those is separated into those likelihood scores. So red or high has a likely score of 75 plus, orange has a likelihood score of 50 to 75, and so on for low and very low. We also have our transportation, so our primary roads and secondary roads on this map. If you scroll in, the visibility for the local roads is set so that it doesn't clutter the map as well. We have our precipitation data there on the right-hand side as well, so people can know how much precipitation is going to come. Then we have our dashboard design. So on the right-hand side there, we have the length of roads affected for primary and secondary and local roads. We also have the map to update or the indicators there on the right-hand side to update as the map zooms in and out, so you can see how much is affected in your little map area. And there's the ability to select by county, and that will zoom to the county on this dashboard. Take a look at one of these catchments. So this was from data that was captured on February 12th. For the 72-hour forecast. This is a catchment in Topanga Canyon in Los Angeles County. This dashboard also includes a nice written pop-up so that people can select on the catchment, and this pop-up will show up and it will be easy to read. So this catchment has a medium likelihood of a debris flow occurring on in the next 3 days and February 12th. The catchment was affected by the Palisades fire that was started earlier this year, and the expected precipitation for the catchment in the next 72 hours is 2 to 2.5 inches. And this was confirmed by a debris flow that occurred on Friday, February 14th in Topanga Canyon. And interesting, this route, SR State Route 27, was closed and is still closed as workers tried to remove debris from the roadway, fix utilities and roadways. Up to 14 1,000 vehicles per day on average come through here. So thought that was a big number. And here's just another photo of that debris flow that happened. Finally concluding, we created an ArcGIS dashboard to identify those recent burn areas where debris flow is likely to occur. The dashboard uses the following: expected precipitation, average slope, and how recent the catchment was burned to calculate how likely a debris flow is to happen. And our audience, the public, utility companies, and local government can use this dashboard to be prepared in the event of a debris flow. Thank you.